Hey, welcome everyone. So last time's AGI discussion forum on the Doug Miles and his Logicmoo work was quite interesting and went on longer than I was able to say, but I caught up afterwards on some of the discussion on video, and it seemed like it'll be beneficial to have Doug go further over some of the aspects of the Logicmoo work. So I asked him if he'd be willing to deliver us Logicmoo Redux and part 2 of the Doug Miles extravaganza. So here we are. I think we'll let Doug get it started with a further presentation on the other aspects of Logicmoo, and then we can plug into further discussion. So yeah, thanks a lot. Thanks a lot for being up for a continuation, Doug.
One of the annoying questions in AI is and can we actually model qualia, which is the sensory experiences that humans are having that are usually kind of subjective. We know that we're experiencing something. We don't know that anyone else experiences things the same way. There's some great philosophical questions about that. But so basically, to create qualia, which is a sensory experience, they need to sequence and take a certain amount of duration each period of time. And so that's why I'm calling it a narrative qualia, because one essential experience follows another one. So we would say that the difference between a program with consciousness and one that doesn't have consciousness is whether or not it's experiencing qualia, whether it's having sensory experience. But a problem with that is by the way, these slides are just my prompting notes. They're not actually probably sometimes on what I'm saying, but this keeps me on track. So if a system was getting 440 hertz coming in through its speaker system, and the program was monitoring that, we would say that it was experiencing it. No, probably not. We're not going to be that pretentious, or no, maybe we are. Where I'm going is that we have to at least expect at some point in our design that the system is experiencing something, and that this is not a biological organism. This is the computer. So the best case that we can have is actually some sort of declarative assertion, something in memory saying, I just heard 440 hertz, and anything beyond that is unrealistic. Yeah, I think this is where I'm actually at. So we sort of have to believe from the get-go that we are capable within our programming system of having the computer experience something. It's not. So let's see. Okay, so in AI, usually the way things are working out in general is people have decision problems that the computer has to solve that are human level, that take human level intelligence. And what they do is they improve its capability of solving those decision problems or a mathematical theorem. But what I think our goal is, if we are actually creating AI or something close to consciousness, is we have to have a computer that is experiencing something. So the odd part here is I'm not actually looking for how many complex theorems can it solve. Like Psych made that sort of does that sort of thing, or how many visual question Q&A things can the program solve, and like at what percentage at a human level. Even though that is an okay definition for human level AGI, I think we need more than the ability just to answer a question. Usually the way that we get away with just being able to answer questions is we can always say, turn whatever the animation pipeline is into what should the computer do next in this situation? What should the robot believe in this situation? And we can make that an iterative query process, and that's fine. And a lot of people are going that direction. Nothing wrong with that. But so anyway, this is about trying to emulate a system and having an experience, because I secretly believe, and I think some of us secretly believe, that AI comes from being in a situation, and enough situations is gaining experience and constructing a narrative out of that experience, and then seeing the world in from that viewpoint, the artificial reality in which it creates for itself. Some of the aspects, probably one of the most important aspects of that, is that let's see, make sure I'm not missing something. Okay, is that our mind projects a lot of our experience into the same place that we are consuming the world from. So if we're doing some sort of visual thinking, let's say it's about something geometric involving shapes, we'll put those shapes in our mind's eye. We might manipulate those shapes, do a little bit of mental rotation, so, whatever it takes within our thinking process. And while we're doing that, we are remembering that we're doing that, and we're experiencing ourselves trying to, like, say, solve a geometric problem. We want to find out if this puzzle piece fits with that puzzle piece. And we don't want to just pick it up and push it there because we're older now. Maybe that's what we did when we were younger. But we want to actually look at the two puzzle pieces and see if they fit together. We are doing a visual, we're in our V6, we're actually recreating the puzzle. And we know that our V4, for example, visual cortex part of the V4, is not receiving it from the real world. And so we know it's our own thought and not a real world thought. Whenever the V6 and the information is being fed in all the way to V5, whenever they match perfectly, or we're getting a sensation of both places having the same visual image, then we know that we're actually seeing what we're imagining. And so, like, the vision system in the human and in animals is syncing their V6 to the same information that's coming in through the earlier parts of the pipeline. So if my V5, V4, and V6 agree, then I'm actually seeing, I'm thinking about actually seeing the right shape. If they mismatch, I need to look a little bit harder at something and get those in sync. But the main point is a lot of our reality is subjectively pushed into our final analysis. So we see the world not just from the sensory point of view, but from the imaginary point of view. And that leads to a lot of optical illusions and so forth, which are interesting. So in Logicmoo, well, first of all, I feel like if we had not done this in the system, we would probably miss something that was more intrinsic to what it takes to cause intelligence. So intelligence itself is, if it's going to emerge from something, it's going to be the fact that we have been able to learn how to predict our environment and so forth. And sometimes that means predicting the sensory world. And okay, so creating what was going to be there in V6, or what we're going to hear, as we said, it's a mental process, and that mental process has to be stored in some format. And so the format that Logicmoo is using is Mentalese, which is an event calculus by Murray Shannon that if we play it into the system, we are imagining, at least as designers, that the system is experiencing it. So we needed a language that those experiences could be played virtually. And that language was Mentalese. So initially, we have a top-down system. So before we have so we have to recognize that what's going to V6 is coming from somewhere, at least at this point, and that's Mentalese. And so, and at some point when we are feeding that V6 data, feeding data into V6, it's top down. It's about what we expect. It may come from some predictive coding, which could be neurologically wired, but maybe I'm probably overstressing this. Okay, well, what's important about this is whatever reality that we are creating in there needs might have a dreamlike quality to it. It's at least experienceable. Also in our bodies, we have more than just the five senses. We have like a perception of where our body is in space. If something is heavy, like my coffee cup, I should be able to, I have a sense of that I'm holding it because I feel the muscles in my arm straining to hold this. Not very hard, but anyway, so a particular sense that I have, or we all have, is that we know our bodily position, and that's called proprioception. Anyway, also we have an idea of like how fast things are moving. If we are, for example, I actually feel the drag of my arm, like as I'm trying to slow my arm down, and I can see how fast I went. So anyway, this is important to realize. There's not just 5 senses. There's multiple senses that are part of our bodily system, and that's something that any kind of a robot that we're building is definitely needs to take into account. But maybe even our virtual world needs to take some of these perceptionary things into account. The Friston, which is kind of like a real neural net guy, sort of described how certain ways we can do some of that wiring. That's what that slide was about, but don't need to go into that. Okay, so in order for something to be called a sense, at least in my thinking, is it has to have a duration. So the event calculus would have some methodology of having like some time experience duration for these things. And so emotions are also kind of a type of sensory input that we have. They might be reactions to the 5 senses, like, you know, you might see something that bothers you or disturbs you, but once you're disturbed by that, and the phone rings and stops ringing, and you think, oh, I wonder what call I missed, you still had in your body those sensations of that you just had moments ago. It's not like they just simply, the phone rang and your mind's off of it, and now your body has no, and you can't remember how you were feeling. No, those feelings are still there. They have a set duration, and all sorts of emotions have duration. So what I want to do is get permission to call emotions a type of sensory input. And then besides senses, there's also other senses that animals have, like they can feel the electromagnetic radiation, to where if a fish is trying to swim home, it knows bodily what it's like when the difference between home and not home, just through a magnetic field. Same with birds. And then we should say that not every sense, even if it is not every sense that we have is always going to be used for making some sort of associative connection, at least consciously. So usually intelligence is how we go from having a sensory world and map it to something like how we move or how we react to that sensory world. So a little robot speeding around the room, 25 miles per hour, that's not bumping into any piece of furniture, we would consider intelligent because it's making decisions to avoid bumping that furniture. But now if that decision was purely a reflex system where it just steered to avoid these objects, we wouldn't necessarily call that intelligence, right? So the point is somehow we think that intelligence means that there is an aspect of an experience and a decision. So that leads to, okay, there are spaces that are not always sensory in that way. Like if I do something to cause myself embarrassment, I'm going to like say feel it. I might say I feel it in my stomach. Someone else might say they feel it in their chest. But it's still somewhat sensory. Like we don't do dumb things, or we don't want to hurt people's feelings because of the way we feel afterwards. It's not because the world is, you know, they take away our toys, that we don't do something mean because we don't like the way it makes us feel when we do that. So some of our behavior is moderated by the prediction of how we're going to feel after we do something. Most of our behavior is. But I want to give an example of something that's non-sensory, because it's important that whatever intelligence structure we have does not always have to be sensorily honed, even though this is. Okay, so if you imagine doing something stupid, and I ask you to do that, you're going to, rather than trying to animate in your head some sort of event calculus of you doing a stupid act, you might just decide that I'm going to forego that and just say, oh, you know, I feel like I did something stupid. Instead of imagining the act, I'm going to imagine the feeling of what it felt like with afterwards. And when you imagine that, you may not actually feel embarrassed or dumb in your imagination at that point, but you have, just like your V6 has a way of predictively encoding something visual, you have another part of you, E6, that is able to emotionally grasp how you'll feel afterwards. So in other words, your mind has, from the neocortex to some sort of a sense organ, has pushed that data the same way as it pushed into V6 into E6. So I'm saying we have wired into us several types of imaginary cortex for buffers. So it makes us capable of imagining something that wouldn't be completely sensory, but I still framed it in a sensory format because I'm saying E6 exists. So there's a lot of things that we do that we're not unaware of. There's a lot of unconscious processing that we have. And one of the ways that we like to hand wave over that, and I don't think it's a hand wave, but one way we like to deal with it is that maybe we have multiple attention systems that are doing some of the side co-processing for us. That perhaps if I'm trying to fit these two puzzle pieces together in V6, that's a lot of mental work for me. I would have to like mentally, if they were offset on the table, I'd have to mentally rotate them together, or I'd have to do this rotation. I don't think that I consciously feel all of that entire process. I think something else does though. I feel like when I very first learned to use puzzle pieces as a child, I feel like I might have sat there and actually rotated them physically in front of myself and saw if they fit. And as I got further along in building more complex puzzles, I was able to not do that with my hands. But at first it took my full consciousness of doing that. And I think when that happened, I may have trained some part of me, a side consciousness, to begin to do and imagine the emulation of that physical process, but in a virtual process. And when I'm doing a puzzle now, I wouldn't be experiencing all of that. I feel like something else, a side consciousness. A side thing is using its entire mental space and actually playing with those puzzle pieces in V6 for me. So in other words, I'm kind of like an executive and I'm saying, I want these two pieces to match, and then some other side consciousness that I have that has its own attention system goes, okay, I'll stop thinking about this and I'll start moving your puzzle pieces for you, Douglas. And does that. I mean, we know how much work it took to do it physically with our hands, and we know that has it's something like that is still going on. We can watch it visually. We may not actually see the rotation, but we get the affirmation that these two pieces will fit together. And then we try to do it physically, and it turns out the thing was wrong, and they don't fit together as well, or maybe they do. Either way, we have to accept that there might be a society of mind inside us that does a lot of our tasks in parallel with us. And a lot of people have, Minsky, Julian Jaynes, myself, we all believe that there was multiple consciousnesses. And it explains a lot of the physical experiences that we have where we aren't thinking very hard, but we're still coming up with these complex deductions. And so I also have the successor hypothesis that maybe the mind is set up with multiple consciousnesses so that if our primary one is damaged or roofied or just damaged, we would be able to still operate. And and these successor consciousnesses share memories with me. So I'm trying to do the puzzle and I'm setting up in my V6 these two pieces, and then it's sharing, the side consciousness is sharing my V6 and then actually does the arrangement for me. Like I don't have to watch it do it, but we have a shared workspace. And and the idea of multiple consciousnesses, each having their own individual workspace, and shared workspaces are fine. And we also have shared memories and experiences. So the side Douglas that's putting together the puzzle has all the same memories I do, or maybe at least all the visual memories that I need to do things. So hopefully it's okay to have moved this to having an idea of secondary consciousnesses within our mind. And some experiments by Gazzaniga proved, beyond the shadow of a doubt, that we do have side consciousnesses. So patients that had their left and right hemispheres separated, he was able to ask, by isolating the hemisphere, the person to do something, and he would say something like, take this block and put it from the left side of the table to the right side of the table. The person would do this, and then he would ask them why they did it, and the person would confabulate a story. I did it because I didn't like the block on that side of the table. I wanted the block to be on the other side. In fact, I thought you were going to ask me that, so I did it without you ever telling me to do that. And so people would confabulate the story of why something was done. And this experiment took on different modalities. Sometimes it was he'd show them a picture of a chicken foot and a beak, and then ask the other one, think of an animal, and the other one would say a chicken, but they had no recollection or memory of being shown chicken parts. So anyway, it is very possible that the mind can have multiple consciousnesses. And this possibility made him start to wonder, are we actually in charge of what we're doing? If we are, say, driving the car to someplace, we may have decided where we're going to drive to, but no, and that's not a good example. If we do something intelligent, we're very likely going to believe that we did it, and it might have been a side consciousness that did it for us. If someone tosses us a pen or a pencil and we actually catch it, we sit there in our mind like, wow, I caught the pencil. I didn't drop it like I did 100 times in 5th grade. I was actually able to catch the ball, and we believe that we did it, and sure, we did. It was somewhere in our brain, but we tend to not. The important thing is we tend to believe and confabulate that we did something intelligent to cause us to catch that ball. And we'll even construct fake memories to say, oh yeah, it was coming and it was really high up in the air and we caught it. And that may or may not have happened. Or maybe it was we might imagine to be happening faster than us. And that's what I'm talking about here. You must take credit for the work of these non-conscious agents. Let's see what is next on here. Wow, we're already at 45 minutes in. So, okay, so yeah, there are senses that, I don't know if there's senses that we don't have any qualia around. Okay, so a high-level topic that's important to understand Logicmoo is most systems like LIDA believe that an autonomous agent must frequently and continually sense its environment, interpret what it senses, and then make action. And this is called the action perception cycle. And you look at all the cognitive platforms, and that's what they are based on, doing the action perception cycle very intelligently. But like in the first presentation, well, before I say that, now Logicmoo is based on the idea that every autonomous agent, be it human, animal, or artificial, neglects its senses, doesn't pay attention to the environment, see that opposite, in favor of a primordial imagined reality. And the disparity between our imagined reality and the reality that's actually out there creates a situation that we end up having intelligent workarounds to arbitrate this problem. And that is something that makes us intelligent. So to do that, we have to procedurally, so to implement something like it, you have to procedurally create the imagined reality, which I talked about before. And so we do something called animatory logic, which is basically an event calculus that creates an almost grounded reality that an animal has or a human has affordances already built up around. So we already know how to catch the ball in our imaginary world, and here's how it goes. A ball comes to us and we just catch it. And that's the level of detail of that animatory logic, at least in my mind. Whereas the realistic sensory world might be more complex and something happened. But at least to my primary consciousness, I have the affordance of catching the ball or the pen when it was thrown to me. And I feel that the format that I'm doing this in, I just described to you as language, but it wasn't language. There was something else that described that action sequence of me seeing a ball coming to me, catching it. And that's what I'm calling mentalese. It's not actually language. And I know it's confusing that it translates to English, and English might translate to mentalese, and that could be done in an automatic process, but I don't want that confusion to lead to believing that this is all done through a what you call a sublingual, the subvocalization loop. There are some people that think the subvocalization loop was important for me to actually imagine a ball coming to me and me catching it. I think what really was important is whatever that mentalese was that made that imagining or that narrative work. So in Logicmoo, we have all of our mentalese translate somewhat to a sensory environment, and it also translates right back to the original mentalese. And how things are learned is sometimes through sensory reproduction. I mean, how things are decided is through sensory reproduction, but how things are learned often is not through a complete sensory recreation. But what my point is that the mentalese itself has to be considered equivalent to sensory to a sensory narrative. So sensory narrative, a video camera catches a visual narrative. And so when I talk about we might have a visual sensory narrative of me catching the ball. I might, but whatever happened in that, I didn't have to go through the time expansion that it took to imagine me doing that. I just can imagine I successfully caught the ball or pen, and that language, whatever it's being used there, I have to give it the credibility of being a sensory language. And my point about showing the 9 senses was to say that there might be credibility to something that's not in the 5. So the idea is that mentally is we're going to have to treat it effectively as if it was sensory qualia. I feel like I have to say that because there's so many difficulties in going, that's not thinking, that's not experiencing. How can you reproduce a human narrative in a robot? It's crazy. We're made up of all these neurons and we don't know how it works. It's fine that we don't know how it works. What's not fine is if we can't reproduce something that at least has the same qualities of that. And that's all we're trying to do is we want a system that effectively proxies for all the stuff that is done there. Okay, so when Piaget, oh my gosh, I never really say these out loud, believes in the process of accommodation and assimilation. And usually how we describe the theory to people is usually some kind of linguistic object doesn't match up to the real world. Like a child will say, look at that doggy. And the mother says, no, that's a horse, not a dog. And the child updates their linguistical store to turn this into a horse instead of a dog. I think a lot that's way too simple. Obviously it is. Linguistics has nothing to do, there's way more going on than linguistics. That's a very high level process. And we're talking about sensory situation, and which is considered a little bit lower. The point is that there is a lot more assimilation going on than accommodation in predictive coding. A lot of times if I see something, I'm going to imagine it the way I project onto my V6, not how it actually really happened. And I'm calling that assimilation, by the way. I'm saying that anytime we fudge or lie to ourselves and we accept sensory input as being what we imagined instead of actually what we experienced, that is a example of assimilation here. So it's not about how we use words, it's about how we use our senses. Do we assimilate that what we just saw was a perfect or was a good enough model, or do we accommodate and go, I need to look at that again because the ball actually flew right, or the pen flew right past my hand. And then I might accommodate, maybe I suck at catching objects. So the idea is that we are, I don't need to say that. So on the slide, I have the agent assimilating as much as possible. So if a man's riding a bicycle, stretches out his arm to make a left turn, the dog that's watching the man actually believes she is perceiving the man to be pointing at something, even though the man is actually making a left turn. So that's an example of her not accommodating that men ride bicycles and make left turns. That's her assimilating, oh, men point at things. That's the assimilation, saying that man's just doing what I think men do. They point at things for me to go and eat, and so, or where they want me to go. So behaviorally, that's possible. For a cat who has a different sort of set of expectations, you might have saw the man on a bicycle, so going left turn, and saw instead what we're seeing here in this image. Sees a man having a great time riding a Roomba, because there's something natural about, or a baby, something natural about our ability to ride animals, and cats have the ability to get on something, have it move, and know it's going to be some sort of an experience, and they can predict that this is what it looks like. So a man on a motorcycle might look like this. So I think my point is that we're really heavy on the assimilation and not the accommodation. And this type of system organizes really well into a hypergraph. We know that like event 1 can take place in event 2, event 3, on to 6, but we also have within our experience the ability to imagine event 1 leading to event 5, to event 4, to event 6. So we can, so these things are hierarchically arranged. I don't know if this has anything to do with the neural structure. I kind of think that have our experiences, and we drill out brand new spaces as we're doing that to create our hypergraph in whatever way our experience tells us to recreate it or to create it. And also, okay, so I think this is kind of the right sequence I wanted to go through. By the way, yeah, it is. Okay. So in order to do this process, we go through two types of modalities, the sensory narrative and the subsensory narrative, if I'm allowed to call it that. The subsensory narrative is just the mentalese that has really tiny little bits of qualia added to each one of those. And we try to re-experience things in little short edits, I would call them. And so the way thinking may happen is that we go from a shorter to a longer to a shorter to a longer version of that. And I would call the mentalese a description of the scene. No, I'm sorry, description of the scene was the opposite. The imperatives that build and edit the scene are the narrative mentalese. And let's see, I already went over the robot here. Oh yeah, I guess this is important. If we did discover an animal that had a sensory modality, well, actually, wait. So I talked about a robot that ran around a room, didn't do any thinking, but yet it didn't hit any furniture. And that robot's not thinking, it's just, it has a pre-wired reactionary sense. And we know that this sort of thing, steering behaviors and so forth, exist in animals probably even without thought, at least we believe they do. So imagine there was another modality that animal could see that we couldn't see. And it was purely using blind reaction or reacted. We would still claim that there was no, like, say, thought going into it. So if there was a sensory world in which we weren't seeing that the animal saw, or what I would say is a narrative that it was following in a reactionary way, we would still not know. We could still claim it was with or without thinking. My point is that I don't think that we're qualified sometimes to decide if there was intelligence in the robot that was avoiding obstacles versus a robot that was avoiding some sort of subsensory obstacles. And because it's a matter of scale. That, let's see if I think that's important to think about. Okay, I see. This is so as something is learning and accommodating the environment, because that's still important. They accommodate through expectation versus what actually happened, and the way that differential is created in the multi-buffer system ends up creating a narrative. Those edits have to physically be made in the neural tissue. I feel like those edits are made with some more mentalese editing the scene until the two scenes are the same. So what's coming into what's in your V5 and what's in your V6, they're not in sync. There are specific edits that are happening to V6 and to V5 that will make those two things in sync, and you'll be able to say, okay, I'm looking at what I'm imagining I'm looking at. And so if you were to take a narrative log or a log of those edits, that would be something that you would remember. You would remember what you had to change about your thinking in order to get those edits to take place there. And so you don't have to remember what was necessarily in V5. You have to remember what led to V5 and then what edits you made afterwards. So primarily what you store there is the way you remember this is through the things that you don't have to save what was on V5. You can save what made you predict the V6 that you predicted, and then what edits did you do to take place. And so I'm saying that there's a sensory accommodation process taking place that we're completely unconscious of that's going on, and it gets us better at getting V6 right the first time. And so you might call this an edit distance between the two structures. Okay, so on the last presentation, I explained something called exemplar coding, and I didn't actually call it that, I don't think, but that's what it is. I have it's a spider, the example of the spider. Imagining he's building a web or wants to build a web, and all he does is model the spider that is in his second person narrative, his E. Oh, we're not going to call it V6 or E6. We're going to call it D6 for doing. So a spider in his D6 was building a web, and he just modeled in his world the same actions. And this allows him to be a little bit dumber and only just follow the instruction book. And this is why I wrote allows Pi-Lang's AIKR, because the intelligence of the spider is going to be based off of his D6 and not his V or not his V5 or whatever. So it's a way of squeezing intelligence into smaller bytes. The narrative system is about doing that. And we have each subsystem uses its own level of convenient detail to keep itself with the assumption of insufficient resources, of knowledge resources within that system. So these, and I guess, yeah, I'll give that description example here. The reason I think this is the case is people are imagining genetically birds would have a bird song like that was programmed in their throat, and then maybe they had a similar program in their ear so that they could make the sound and then hear the sound and then, you know, connect up or whatever, hook up. I think that particular knowledge is stored in the same place on the male and the female bird. And so when the male bird wants to actually make a bird song, he's copying some sort of a memory of the song and comparing how well he does at matching his own personal memory of the song. And then the girl bird compares his song to her dream bird, the bird, you know, the song that she hears in her own head, and goes, wow, it was destiny for us to be together. So the idea is that that these animals probably have a sensory detailed memory. And that's why I got, you know, that's why I went with how I did with the spider building the web. It's a sub-sensory, semi-sensory, or full sensory memory that these birds are born with of a bird song. And then when they are living their life, they are, like I said, the guy's copying, the girl's listening for that copy. And I think almost all these subsystems, these multiple minds, are working on their own, from their own modality and level of detail. And not every reason I was trying to give the example of a sense X here is not every modality has a physical 5 sense or 7 sense example modality. They can be on wherever they are. We don't know how many minor senses that we've virtually created within the organism of the brain. And if there are little individual agents in the brain, they might have their own sensory channels that have nothing to do with the outside world. They might be reacting to something that we don't ever get a conscious chance to experience, but we end up getting the aggregated result of these agents living in their little virtual spaces into our conscious mind sometimes. And sometimes they'll act and do something for us, and we will believe that we thought of it. And so there's the user illusion that we don't always, just don't obviously have a full view of it, but we have enough technology that if we did have a full view of it, we could try to at least create some of these. And that's not too outlandish. Let's see. So how am I on time, and what questions so far exist? Okay, so the whole point of
on time, we have gone through a lot of time, and it's been interesting. I think yeah, if folks have questions or discussion points, it would be timely to jump into them soon. And on the other hand, if you have 1 or 2 key points you want to make before wrapping up the lecture portion, that'd be cool too.
Okay, I might, yeah, hopefully I have, like, yeah, I have 4 slides left. Okay. Okay, so I would say that you know, the theory ascribes to the fact that there's multiple imagination buffers called Cartesian theaters. And these sub-agents or side agents, I haven't decided what they should be called, they may each have their own, and that's fine. Okay, maybe we look at effects. Okay, so we are usually only aware of our inner mental leads, the one that's in our primary consciousness. that is the one that actually describes where we've been and what we're doing, what we thought about. And that's sometimes called the autobiographical self. And I feel like that autobiography is transcribable into a mentalese language, which is a tokenized event calculus. It may only remember what I did, not what I would, or it may remember what I was thinking about. And it might not remember both of those, but one leads to the other. So the transcription that gets stored in my autobiographical self may only contain why I did things, not how I did things. And from either one, I can construct the other one. And so that's a lot of how false like sensory memories could take place. We generally, instead of selecting something that is going to be the most rewarding, we're more likely to select the most plausible transition around the mentalese. So mentalese is a serialized set of things going on that we have to, whatever we did, we have to choose what the next one is going to be. And we have to fill up our time with some sort of a memory or a narrative, just as we exist, because we're used to needing, we can't necessarily deal with mental silence. And so we have religions and meditations and so forth that will help us learn to cope with mental silence, the silencing of the monkey mind or whatever. That's always around telling us things. But anyway, usually we're not going for reward, we're going for plausibility. And there is a certain reward system out of plausibility that is just fine to put there. So the reason that we do this is it causes compression and so forth. And if I have a narrative of that is really complex sensorily, maybe one of my other side consciousnesses will look at that narrative and write it much simpler for me, and have the experience and record my experience as its experience. And then when I'm later on trying to recall something, I only have to deal with its experience. So this cacophony of society of mind system is actually what consolidates our memories for us. That's a possibility anyway. That's why I'm saying we constantly unintentionally consolidate each other's memory, the society of mind agents. And oh yeah, we definitely have a reward system of, we don't want memories or narratives that will cause us a lot of anguish. We actually grow, I think it's important to recognize that we grow an affinity to hearing ourselves think or hearing ourselves talk or whatever it is, our ability to visualize. We actually enjoy that process, and we get a chemical reward from these things. And we attach meaning to the various parts. So yeah, I saw that just trying to get this covered was going to take out time from having the ability to really show how each one of these little pieces are running individually, except for at least the first video, we got to see an example of a very high level version of confabulation. But I think this confabulation happens on all levels. That confabulation happens on all levels. And we end up being who we are from these things. And the important point I need to make is that a lot of things that we are doing are scripted, or at least done by a side conscious. And that makes, and we can grow attached to letting that side consciousness do something for us. Like when it caught the pen, I was very happy. So I'm going to let whatever part of my brain that I was used at that point, my auto to do pen catching in the future. Okay, so that's the presentation. And so I'm ready for questions and so forth.
Yeah, so this is all, it's all interesting, and there's I mean, of course, I'm led to thinking about to what extent this is stuff that's there or isn't there in our OpenCog approaches to embodied learning and Minecraft game world learning and robot and metaverse-based learning in general. I think what Nil is doing now in the Proto-AGI project, which we'll present in this AGI discussion series sometime, is really more pure temporal reasoning, planning, and pattern mining without a sort of simulation in the sort of imaginary mind's eye theater aspect. Now in Engineering General Intelligence, our not long ago book on the OpenCoggy approaches to AGI, we there was a short chapter on simulation, right? Which, I mean, basically, we posited that doing simulation concurrently, sort of, and coupled with reasoning was going to be important, and that simulation and reasoning would be useful for answering different questions, that simulations could be used to sort of estimate the truth values of hypotheses conceived by reasoning in a cheaper way than doing physical actions, and also that like data mining the results of simulations or pattern mining results of simulations could lead to hypotheses to be fed into reasoning. Recently, I've seen various papers popping up, like deep neural net and probabilistic reasoning people from mainstream AI establishment somehow discovering that simulation may be useful, right? And talking about this also in the context of using game engines for simulation, so that the mind's eye is a game engine. And we did stuff like this in 2007 or something in Novamente Cognition Engine, like you're having Novamente learn to control little animals in a virtual world, but then have a separate copy of the game engine that it could run to do simulations of what was in the virtual world. And then a more modern extension of that, like now there are neural nets being used to do sort of accelerated simulation of what happens in physics engines, right? So your mind's eye game engine wouldn't have to literally be a game engine. Your mind's eye game engine could be a neural net trained on a game engine, or you could have multiple nets optimized to simulate different sorts of scenarios in a game engine or something. So I guess with all that as context, what I'm bouncing around in my mind is whether for human-like AGI, there's the need for a cognitive component besides reasoning, like inductive, abductive, deductive, temporal reasoning, and realistic sort of literal simulation, like you would do with a game engine in your mind's eye, or a neural simulation in the mind's eye. Like, is there really a need for sort of looser mind's eye simulation? Like in the example of mental rotation, it feels to me like I have a looser mind's eye simulation. It's not just logical reasoning. It's also not accurate enough that it could be like a good game engine in my head figuring out, but it's some kind of visual thing. And when I think in my mind's eye about, say, the relation between a topos and a topology, or some abstract mathematical thing, which is kind of spatial and geometric-ish, but not exactly geometric. I mean, I do have a visualization and some internal theater of like limit points approaching a limit, and then like more fuzzier, higher dimensional limit points approaching a limit. But I'm not sure what is that internal mental theater, and it can be dynamic too, right? It's a kind of a simulation, yet not as concrete, detailed, or realistic as what I would most immediately think you'd get from like simulation in a game engine or something. And I guess you're pointing in a similar direction, right? But what I'm trying to think through is like what lessons to get from your work on what are the properties of this, like, semi-realistic, yet still in some sense geometric, topological, and quasi-visual simulation facility that humans do seem to have, and that presumably when you sort out the neuroscience of this, there's like connections into visual cortex and into, the portions of the cortex even with abstract thinking, and these are somehow coming together to form some abstract visualization thingy. So I mean,
it's such a healthy question that you're asking, because I mean, one of the things are how much idiomatic logical steps does this thing need to make, versus is there sort of a stochastic way of sometimes foregoing all this like extra business of like actually forming a small visualization of something or whatever it is. It's like, it's such a healthy question, because it seems like it might be too much work to sometimes frame everything in the simulation recreation format. It wouldn't seem adequate, or if it would have to be pretty fast. But how many things do we cheat on stochastically and create like that we could do with a neural net that would emulate this simulation type structure. And what we have to ask ourselves is, will the neural net actually create the simulation structure that it would have had to create to be able to get the problem solved? And in some cases, it's going to be no, it didn't meta imagine. But some cases we could think that it could, or that it did it virtually. We just didn't have a virtual world temporary stopgap that we're able to tease out of it. But it may still have done all the same things mentally that we humans do. And a lot of this comes from, you know, the Hebbian point of view that, wow, we are doing all these things. And I guess what the important part will be is if that neural net will actually emerge whatever quality within itself to actually do effectively some of the things that we do, even if it doesn't simulate it in any kind of neurons but so yeah, it's such a healthy question. Well, how much does a simulator have to look like a simulator or not?
Well, and how much plus may we get from inaccurate simulation sometimes, right? Like if I'm thinking about topological spaces that are not geometric, I mean, as a math example, and of course not everyone's a mathematician, but if you're thinking about something like that, you may not want an exact 3D simulator. I mean, the 3D geometry is misleading in a way, but yet you're still dealing with a kind of spatialish positioning of things and paths. And say, think about like homotopy type theory and the you know, the category of paths of identity proofs or something. I mean, this is geometric in a way.
It is,
you're both led and misled by visualizing paths in proof space as physical paths through 3D space. So the fact that the simulation leaves out some aspects of what a physics engine does is a feature there, not necessarily a bug. And there are probably examples of that in non-technical imagination also, even though since I think about math a lot, I'm tending to land on those examples. Like if you're trying to visualize a social network or a graph or something, just a network of all the people that you know and relate to. This is a graph. Embedding the graph into 2 or 3 dimensions is sometimes useful, but introduces some distortions. And you might want to hold the graph nodes and relations in your mind somehow in a way that doesn't commit on the precise coordinates. On the other hand, it does leverage something about the spatialization there.
Yeah, we'd be making a mistake to try to make everything fit through a spatial thing, even when it does conveniently do that. It doesn't always, like if I'm trying to like visualize a social network, for example, I'll kind of like just in time late found and visualize, oh, there's a connection between this person and that person. Like I won't ever just see the whole, I doubt that the whole social network is constructed geometrically in front of me, you know, like all the little pieces, but I'll just imagine every once in a while, there's this guy knows this guy, and I'll have like maybe 3 steps in the arc, you know, three nodes or something. And yeah, so that's a good example of where but yeah, there's a spatial component that we can't deny, and it looks like a graph, and we get excited by graphs because it looks like something we can start to do topological analysis on and so forth. Yeah, but I do know this. I mean, I couldn't answer. I do know that if we don't do sometimes, if we're incapable of that activity, then we've done something wrong. We have to have a system that's at least that capable sometimes to make certain types of thinking get done. And about that inaccuracy part, I think the inaccuracy is important because it allows us to make deductions that we wouldn't have otherwise made. That we have to be able to represent things in less detail than the perfect geometry of it. And we have to be able to make mistakes geometrically in our thinking in order to get anything right. And the simulator doesn't necessarily afford all those mistakes that we have that are useful. So one of the important aspects of mentalese is you could take something that's like 15 steps and compress it down to 7 steps. And that has to be done really cheaply in a way that allows it to miss important things. In order to make an analogy, it's usually done by information loss. But the idea was it would be done at runtime, or it would be done at that moment, at the moment of comparison, rather than at the moment of learning about something. So you don't, but when you learn something, you still might learn it in a compressed way, and then you have these automatic expanders that take your 7-step mental narrative and turn it into a 25-step narrative. And that same 7 can be compared to this 9 because we have the ability to convert the 7 to 9 rather than always converting the 9 to the 7. So the inaccuracy is usually ideally stored in the most parsimonious, smallest way. We get inaccuracy by storing it really small and then trying to get things to fit outward. So if I have these two things that look like they don't fit and I need to do some prime factorization, you know, the 4 and 7, the only way they're going to relate together is by 12. I mean, 4 and 3, they're only going to relate once I turn the 4 into 12 and the 3 into 12. And then hopefully the analogy will fit there, you know, rather than to shrink the 4 to the 3 to get the analogy out of there. But I think both ways are okay. And I'm saying that that's from the simulation level, a legal thing to do. And we don't actually have to physically simulate it. And that was, we just have to textually or through our data structure has to at least convert to these comparable things. You know, I just was keeping a very tight relationship between the data structure and what a simulator would have to do to simulate. Yeah, the system is designed for inaccuracy, and part of that inaccuracy was like it simulates more than it ever accommodates. And to like say that this assimilation process of the inaccuracy has to be weaponized into something that happens because otherwise it wouldn't scale. The only way that, I mean, how we exist in our world is we create these really simplistic narratives, and we feel like those are realistic enough to do whatever thinking we're doing, whether it be visual or not. Yeah, but it's a good, interesting question if this can be done also via neural net. And I'm just going to say that as long as our neural net has the ability to get idiomatic or experiential when a part of a type of thinking actually needed it to do that for us.
Yeah, I mean, anything could be done by a neural net in principle, but given that it's like Turing complete, blah, 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 but whether it's convenient to do